Okay, so in Chapter 9, Lesson 1, we're going to learn about the basics of quadratic functions. This entire chapter, Chapter 9, is all about quadratic functions. Section 1 is the basic foundation for the rest of the chapter, so it has a lot of important information. If you'll look at the top paragraph on your notes, it says the function y equals x squared is shown in the graph. Notice that the graph is not linear. This function is a quadratic function. A quadratic function is any function that can be written in the standard form y equals ax squared plus bx plus c, where a, b, and c are real numbers and a does not equal 0. The function y equals x squared can be written as y equals 1x squared plus 0x plus 0, where a equals 1, b equals 0, and c equals 0. So the most important thing from that paragraph is the equation y equals ax squared plus bx plus c. Like it says, this is the standard form of quadratic equations. The bx and the c are optional. Some quadratic equations will have those values, some will not. But the ax squared is not optional. All quadratic functions have to have an x squared value. That's what makes them quadratic in the first place. So if this value is not present, then it is not a quadratic function. In the next paragraph, it says, in Lesson 5.1, you identified linear functions by finding a constant change in x corresponded to a constant change in y. The differences between y values for a constant change in x values are called first differences. Notice that the quadratic function y equals x squared does not have constant first differences. It has constant second differences. This is true for all quadratic functions. So when you're looking at a set of ordered pairs and you're trying to determine whether or not that set of ordered pairs is quadratic, you're looking for what's called second differences. As you'll notice by this image or this table of values, the difference in the y values is plus 1, plus 3, plus 5, plus 7. What we're looking for is almost like this second tier of a pattern, that these numbers have a constant change of plus 2. That's called second difference, and that's what we're looking for in a quadratic function. So the examples at the bottom say, tell whether the function is quadratic and explain. So notice, you have to be able to tell whether a function is quadratic by looking at both its ordered pairs and by looking at its equation. So let's look at the ordered pairs first. To tell if a function is quadratic looking at the ordered pairs, you're looking for what we talked about up here, a second difference. The first thing you want to do is just quickly double check that the x values do have a constant change. Because if they don't have a constant change, then you won't see a pattern no matter what. In these x values, do we have a constant change? Yes. What is it? Plus 1. Now, the most important part is looking at the y values. You're looking for a constant second difference in the y values. So look at the first difference first. What is the difference between negative 9 and negative 2? Plus 7. Between negative 2 and negative 1? Between negative 1 and 0? And between 0 and 7. Now, we're not concerned with this number being the same. We need to go one more step. We're looking for the difference between these numbers to be the same. What's the difference in positive 7 and positive 1? Positive 6 or negative 6? That's decreasing by 6. What's the difference between 1 and 1? 1 and 7? Positive 1 to 7 plus 6. So are these numbers the same? No. So this does not have a constant second difference, which is why it's not quadratic. If it was quadratic, then all of these numbers would be the same. Okay, look at the next example. Again, the first thing you want to do is just quickly double check that the x values are showing a constant change. Because if they don't show a constant change, you're not going to be able to see the pattern even if there is one. Do these x values have a constant change?
Yes.
Again, it's plus 1, just like last time. So now let's look at the y values. What's the change between positive 4 and positive 1? Between 1 and 0? Between 0 and 1? And between 1 and 4? Okay, now go one more step. What's the change between negative 3 and negative 1? Between negative 1 and positive 1? And between positive 1 and positive 3. So do we see the constant second difference that we're looking for? Yes. So that's why this is a quadratic function. Okay, y equals 7x plus 3. Now all we have is the equation. We need to decide whether or not it's quadratic just by looking at the equation. So to tell if it's quadratic, you need to look back at standard form of a quadratic equation, which is y equals ax squared plus bx plus c. So what do y'all think? Is y equals 7x plus 3 quadratic?
No.
No. Right. It is not quadratic because it does not have an ax squared value. A quadratic function has to have a power of 2 in it. Does anyone know what kind of function this is? Linear. Linear functions have a power of 1. Quadratic functions have a power of 2. So that's a linear function, not a quadratic function. How about the next one? Y minus 10x squared equals 9. Yes. I can tell that that is quadratic simply because it has the power of 2, and that's what I'm looking for.
Doesn't it also have a y in it? Or,
Yes. Okay, if you'll flip to the back side of that page. At the top it says the graph of a quadratic function is a curve called a parabola. To graph a quadratic function, generate enough ordered pairs to see the shape of the parabola, then connect the points with a smooth curve. So this word parabola is something you need to add to your vocabulary. That is the shape that quadratic functions make when you plot them on the graph. Okay, it's that U shape that we've talked about before. It's called a parabola. Under that it says use a table of values to graph the quadratic function. So this is where you need your graph paper. We're going to graph a couple of these quadratic functions. Graphing quadratic functions is no different than graphing linear functions that we've done in the past. You're going to take the equation that's given to you, and like the instructions say, you're going to use a table of values, which means you're going to choose values for x. You're going to use the given equation, and you're going to plug in those values of x to generate values for y. Now, just like when we graphed linear functions, you need to choose 2 negative values, 0, and 2 positive values. The standard values that we use normally are -2, -1, 0, 1, and 2. As long as there are no fractions in the equation, these are probably the easiest values to choose. However, if there is a fraction present in the equation, then you may want to choose other values to make the problem easier. But as long as there's no fraction, these are usually the standard x values we use. One thing important for you to notice is that when you plug in a negative number for x, it should be in parentheses. Why does that matter? Because of the negative sign. A negative number in parentheses to the power of 2 is different than a negative number not in parentheses. When you plug in a number for x, it should be in parentheses. Now, you can either do that in your head or you can use your calculator. If you do use your calculator, make sure that you type the parentheses just like we wrote it down. Because again, if you do not use parentheses, the sign of your answer is going to be wrong. So when you type it in, you need to use the parentheses on the calculator just like we wrote it down. So either in your head or on the calculator, what is -4 times -2 squared?
8. Oh wait, -2 squared. -16.
Negative 16. Keep going down the list, just plugging in your different x values. -4 times -1 squared is what? -4. -4 times 0 squared. -4 times 1 squared.
4.
-4. And -4 times 2 squared.
-16.
Now that I have my ordered pairs, I need to just plot those points. So draw your coordinate plane. In this case, since my y values get kind of large, I'm going to count my y values in multiples of 2, which will just help my graph from not having to be so large. And then just plot those 5 points, -2, -16. -1, -4. Once you have all 5 points plotted, you need to connect the points to create your smooth curve. Let's try the next example. It says y equals x squared plus 2. So I'm graphing this using a table of values, which means I'm going to choose values of x, plug them into the equation, and calculate for y. So again, since this equation doesn't give me any kind of fractions, I can go ahead and use the standard x values, -2, -1, 0, 1, and 2. And all I have to do is plug those into the equation to figure out what y is. So what's -2 squared plus 2?
6.
Good. -1 squared plus 2?
3.
0 squared plus 2? 1 squared plus 2? And 2 squared plus 2. Once you have all 5 points, go ahead and draw your coordinate plane and then just plot those points. Make sure that when you're connecting your points, you're creating a U-like shape and not a V shape. The only reason sometimes these look like a V is because we don't have very many points. If we were to graph more points, we'd be able to see the curve more clearly. But they always should make a curved U type shape, not a V shape. So the only real difference between graphing these and graphing linear equations is the shape you get on the graph. When we graphed linear equations, we got a line. We graph quadratic equations, we get a parabola. If you are not getting a parabola, either you've plotted your points wrong or you did a calculation wrong. But quadratic equations will always create the same shape of a parabola. If you'll set your graphs aside for just 1 second and look at this paragraph. We're going to skip the third graph for now. It says, as shown in the graph, some parabolas open upward and some open downward. Notice the only difference between the two equations is the value of a. When a quadratic function is written in the form y equals ax squared plus bx plus c, the value of a determines the direction a parabola opens. So, as you can see in those two examples we graphed, sometimes parabolas open down, sometimes they open up. The value of a is how we can tell whether the parabola should open up or down. So look at the first example where the parabola opened down. What was the value of a in the equation? Look at the second example where the parabola opened upward. What is the value of a? So what do you think we can tell about a and how it affects the direction of the parabola? Yes, if a is negative, the parabola will open down. If a is positive, the parabola will open up. Now, notice, just like this paragraph says, this only works if it's written in standard form. So, on problems like these three at the bottom, you cannot tell the direction of the parabola unless it's written in standard form. So, for example, y minus 1/3 x squared equals x minus 3. We may be tempted to say that this parabola is going to open down because when we look at this equation, 1/3 is negative. However, the problem is this equation is not in standard form. If it was in standard form, then y would be by itself. So how are we going to get y by itself?
Add 1/3 x to the first one.
Good. So I get y equals 1/3 x squared plus x minus 3. So now I can see that the value of a is what? 1/3. Which means this parabola is going to open in what direction? Upward, yes. What's the value of a in the second example?
-3.
Good, -3, which means this parabola is going to open downward. What's the value of a in the third example?
-4.
Good, which means this parabola is going to open downward. All right, last thing from this section, if you'll turn to the very last page. Couple more things we have to know about parabolas. The first thing is called the vertex. The highest or lowest point on a parabola is the vertex. If a parabola opens upward, the vertex is the lowest point. If a parabola opens downward, the vertex is the highest point. Parabolas also have what are called minimum and maximum values. If a is greater than 0, so basically if a is positive, the parabola opens upward and the y value of the vertex is the minimum value of the function. So look at the example here. The vertex here is at the bottom of the parabola, which is why the y value of the vertex is the minimum because it's at the very bottom. Over here, if a is less than 0, the parabola opens downward and the y value of the vertex is the maximum value of the function. So in this example, the vertex is the 0.35, which means the maximum is 5 because it's at the top of the parabola. So look at the last 4 examples. It says identify the vertex of each parabola, then give the minimum or maximum value of the function. So the first thing, to identify the vertex, you just find the point at the center of the parabola and tell what that ordered pair is. So what is the ordered pair of the vertex in the first example? -3, 2. So the vertex is an ordered pair, -3, 2. DJ, you need to sit up and pay attention, please. Now, to tell whether the graph has a minimum or maximum, all you have to do is ask yourself, is the vertex at the top of the graph or the bottom of the graph? Yes, the vertex in this example is at the bottom of the graph. So does the vertex represent the minimum of the graph or the maximum of the graph? The minimum. The minimum is just the y value of the vertex, so the minimum in this case is 2. In the top right-hand example, what is the vertex? What's the ordered pair of the vertex? Good, 2, 5. Ask yourself, is the vertex at the top of this graph or the bottom of this graph? Top. So does it represent the minimum or maximum? Maximum. So the maximum in this case is 5. Okay, Tara, what's the vertex of the third example?
-2, 5.
Good. And Drew, does that represent the minimum or maximum? So the maximum is what? Good. Last example, Jack, what's the vertex of that parabola?
3, -1.
Good. And Shannon, does the vertex represent the minimum or the maximum? Good. So the minimum in that case is what? -1.